coming up, and that's on exploring domain-specific architectures for network protocol processing by Artem. I hope I'm pronouncing your name right. Artem, you should have the ability to share your material and also share your screen and unmute and talk. And hang on,
Hello.
I will promote Antoine as well. As your
Thank you.
Yep. Okay, so he should have just
Artem is
gotten
coming
the
from space.
Yeah, I love it, Artem. This is great. Like, what time is it up there?
Oh, it's night, almost.
Okay, sorry about that. We're having some technical issues here.
All right, well, you all sound fine to me, so take it away.
Okay, can you see the screen?
Yes, we do.
Okay, then I'll mute myself and play the video.
Hello, I'm Artem Agiev, and I'm a doctoral student at Max Planck Institute for Software Systems. Antoine Kaufmann is my advisor. In this talk, I would like to tell you a bit about our ongoing work on exploring architectures for flexible network protocol offload in the cloud. Modern cloud applications commonly incur protocol processing bottlenecks. With increasingly distributed applications and computational accelerators, individual hosts need to send and receive more data. Luckily, network speeds are still growing rapidly, providing more capacity. However, the protocol processing to transfer data between applications and the network consumes more and more precious processor cycles. At this point, you may ask, does RDMA not solve exactly this problem? With RDMA, systems communicate via memory-to-memory transfers implemented directly in the NIC hardware. And when RDMA is a good fit, these systems do great in terms of cost, performance, and power consumption. However, RDMA lacks flexibility to modify the protocol stack because of the fixed hardware implementation. And much recent work shows the benefit of different and often customized protocols and interfaces for different applications. Programmable smart NICs provide flexibility but have other drawbacks. Smart NICs come in two flavors, multi-core NPUs and the FPGAs. NPUs perform well on highly parallel tasks and feature a familiar software programming model. However, they rely on parallelism across many cores for performance, a problem for the often inherently sequential protocols. And as they also use processors, they often do not substantially improve energy efficiency over software processing. FPGAs are much more flexible and support a wide range of hardware designs. But this flexibility comes at the cost of increased chip area, which translates to high per unit cost, and lower clock frequencies compared to ASICs. So what is the solution? Is there a protocol processing offload architecture that is flexible, fast, and efficient in terms of area and power? This is the question we set out to answer, and quickly found that finding an answer is complicated. In the rest of this talk, I will introduce our ongoing work towards answering this question. We found three technical challenges while trying to find an answer to this question. First, design space for flexible protocol processing architectures is large and mostly unexplored. While there exist a few SmartNIC architectures, they only cover very specific design points. As a result, there are only few reference points for making design decisions. Next, even after picking concrete architecture designs, evaluating them is difficult. For evaluation, we need to measure the overall system performance and energy consumption under a real workload. However, taping out even a single design takes a considerable amount of time and resources. Comparing a larger number of designs by taping them out is completely infeasible. Finally, different architectures often support different subsets of protocols and offloads. Some may support fewer protocols, but with much greater efficiency. This introduces yet another dimension to the evaluation. To address some of these challenges, we take inspiration from machine learning accelerators. Domain-specific architectures, DSAs for short, have revolutionized machine learning. Instead of general-purpose cores or fixed algorithms, these architectures provide domain-specific primitives for specific classes of applications. Systems like Google's TPU, on the right here, bring order of magnitude improvements for performance, power efficiency, and cost. But the second key element for success of these systems are domain-specific programming abstractions. They capture the algorithmic application semantics while abstracting away specific implementation details. A TensorFlow model can be compiled to run efficiently on a CPU, GPU, or a TPU alike. These abstractions decouple applications from hardware and allow both to evolve independently. We leverage similar ideas for network protocol processing in our framework, kugelblitz. Here's an overview. We start with separate hardware architecture and protocol specifications that serve as inputs to the rest of our tools. From high-level hardware specification, we generate RTL for simulation and synthesis targeting FPGAs and ASICs. Separately, the compiler takes a protocol as an input and generates a runtime configuration for the provided hardware specification. This combination allows us to quickly generate real hardware implementations and determine which input protocols they support. Let's start talking about the hardware side. Here is the overall hardware architecture. For now, kugelblitz operates as a bump-and-aware network processor. It sits in between the MAC on the network side and the existing NIC logic. The outer blocks in blue, the parsers, deparsers, and packet buffers, are mostly fixed, while the inner core, in green, composed of the processing pipelines and state memory, is configurable via the hardware specification. Let's talk about those hardware specifications. Here we describe different architectures by instantiating and connecting the following components. Routing elements select one of the configured inputs depending on the concrete runtime configuration loaded. Pipeline registers have a configured width and a routing element for obtaining the input value. For ALUs, the specification lists the operations to support, and the runtime configuration picks which one to use. Finally, we have state access components for CAM lookups and regular state memory. Overall, the hardware spec describes the superset of possible behaviors, while the runtime configuration, which is highlighted in green, configures routing and the ALUs to implement a specific protocol. Now let's take a look at an example. Let's take a look at the graphical representation of the configuration file using the inspector tool. To the right, there are blocks to capture the outputs of the pipeline. They are two of the special blocks. The one on the bottom is the state write. The number of inputs and the shape of each input depend on the state description. The one on top is the interface to the deparser. It has a large number of inputs because it receives the command and every byte of the prefix from the pipeline in order to construct the outgoing packet. Registers are organized in banks. Every register's width and inputs are configurable. The input set defines the physical connections, one of which is selected at runtime according to the runtime program. The ALUs are the main processing elements in the pipeline. In order to describe an ALU, we need to provide its output width, latency, and the instruction set. Each ALU has its own instruction set. This helps to fine-tune the utilization. Immediates are just a way to represent constants. The inputs to the pipeline also come from a special block that interfaces with the parser. Naturally, its characteristics can also be tuned to match the requirements. The hardware generator then takes this specification and transforms it into RTL. This step is completely automated. First, we instantiate RTL implementations for each component and then connect them together according to the specification. Chisel proved to work great for this, as we can leverage general Scala features for metaprogramming while using Chisel as HDL. The resulting hardware definition can then be given to FPGA or ASIC synthesis tools or be simulated. Here is a concrete example of a protocol specification implementing a NAT with a checksum update. The gray blocks here represent constants, the green blocks represent arithmetical and logical operations, the purple and blue blocks represent special nodes. and the silver node to the right is a conditional. The operations to the top left verify if we are dealing with TCP/IP packet. The lookup table access and the state read on the bottom of the image get the pre-computed checksum correction for this flow. The arithmetical operations on top compute the new correct checksum, while the conditional decides either to forward the original packet or its modified version. The operations to update the other fields of the packet are not included for simplicity. Now let's switch gears a bit and talk about the other half of the story, protocol specifications. Here our goal is to capture protocol functionality at an abstract level, without binding to a concrete implementation choices. This allows us to efficiently compile protocols for a variety of hardware architectures. Our protocol specifications comprise two parts: state declarations and data flow graphs. The state declarations specify multiple lookup tables and array instances. Lookup tables are read-only for protocols and are used, for example, for flow lookups. Arrays can be read and written and can store flow state. We describe the actual processing as two data flow graphs for receive and transmit processing. Data flow graphs are ideal for our purposes as they only describe data dependencies without forcing additional ordering. They also directly expose available parallelism in the protocol and additional information such as the length of critical paths. Now let's have a look at the real protocol. Finally, we want to take an abstract protocol specification and use it to configure a specific hardware architecture. For this, we have designed a compiler that takes both the hardware and the protocol specifications as input. Our compiler first converts the hardware specification into a graph, and next it searches for a feasible mapping of the protocol graph to the hardware graph. The output is a specific configuration for each routing element and each ALU. Our current implementation of the compiler performs the search using a set solver, after translating the mapping into a Boolean satisfaction problem. Of course, this process may fail if the given hardware configuration cannot fit the protocol graph. To recap, we can now generate hardware implementations and map protocols to them, so it's time for evaluation. Here we run into the challenge discussed earlier. What we want to evaluate is really full system end-to-end performance. But even now that we are able to automatically generate RTL for different hardware configurations, taping out and fabricating each design as a chip is not feasible. All we can hope to achieve is to get as close as possible to this. We do this by combining three separate components in our evaluation. First, we synthesize the generated RTL with VLSI tooling to obtain timing and area numbers. Next, we plug our RTL into full system simulation with multiple hosts, simulating the full host, including OS and applications. For the simulations, we use timing parameters from earlier synthesis. We also collect simulation traces from end-to-end and for more accurate VLSI power analysis. Finally, we also deploy the RTL on an FPGA for testing in a real system, but with a lower clock frequency, to validate our simulation results. An additional question we want to answer in our evaluation is the cost of the flexibility that we introduce. For this, we have built an additional tool, the fixed hardware generator. This tool takes a protocol specification as an input and generates a fixed hardware specification. The fixed specification only implements exactly this protocol without any flexibility for runtime configuration. We can convert these hardware specifications to RTL using the rest of our tooling. With this, we can now directly compare the performance and area cost when comparing to flexible configurations running the same protocol. Finally, while much of this work is still ongoing, we do have some initial confirmation that all of this actually works. The main construction site at the moment is our compiler, where support for stateful memory is still incomplete. But fixed hardware specifications work correctly, both in simulation and on the FPGA. For both, we integrate the generated RTL into the random open source FPGA NIC. We simulate Kugelblitz hardware designs as part of a full system using the Simbrix simulation framework, also developed in our group. In Simbrix, we run RTL simulations of the combined Kugelblitz and Corandom RTL with QEMU and Gem5 and network simulators to simulate two separate hosts connected back to back. We have tested this with two relatively simple protocols, the net we saw earlier and the firewall. Finally, we have also synthesized and implemented the combined RTL on a Xilinx FPGA board and tested it in our physical testbed. To summarize, in this talk I have told you how we are using Google Blitz to enable effective design exploration for flexible offload. The key ideas in Google Blitz are to combine abstract protocol definitions with high-level hardware configurations and generate RTO from those hardware specifications and then automatically compile protocols for those hardware designs. As this work is relatively early stage, there are many remaining challenges. First, using RTL generated from Google Blitz in VLSI synthesis tools to obtain timing, area, and power estimates, as Google Blitz ultimately targets ASICs. Next, we are interested in leveraging program synthesis techniques to enable more flexible mapping of protocol graphs to hardware, beyond one-to-one mapping. Finally, we plan to integrate a DMA engine into Google Blitz to turn it into a complete NIC.
Okay, that's the end.
Great, thank you. All right, questions and hopefully answers. I know I have one. So have you tried synthesizing this and putting it on an FPGA, for example, like as a test run?
To some extent, yes. We are still in the early stages, so we have to deal with the fact like sometimes we have routing problems. So like, for example, we need to limit, for example, like cam depth sometimes, or the MTU needs to be limited a little bit, because otherwise it never completes routing, or it cannot complete routing at all.
Okay, but ultimately you're targeting an ASIC type implementation, you said.
Yes, because otherwise we already we introduce flexibility, so with FPGA we'll be paying for flexibility twice, and there is no real reason to deploy this on FPGA because it's already flexible.
Yeah, except that ASICs sometimes are expensive, right? They can be quite expensive. What's the turnaround time to make one of these designs and synthesize it and implement it? Like, what do you think is the turnaround time?
Much like I think the bottleneck here usually it's FPGA tools or.
So it's really just the tooling.
Yeah, sometimes, I mean, if we don't consider the development times, yeah, our tools are quite fast. So, I mean.
Okay, cool. Yeah, it's very interesting. Any other questions? Okay, I see one. Yeah, do you have any insights so far regarding the cost of this flexibility that you're trying to introduce?
This is
what are the
a very
pros
hard
and
question.
cons?
This is a very hard question because the main question here is how much flexibility do we introduce? Because we have tooling to produce just fixed hardware. We can merge different configurations, so we are sure that they're running two or n protocols. Then but then we can try to future-proof a configuration and try to say, okay, we want it to be more flexible than we really need right now, but then it really depends on the flexibility. Usually, if you're going for something very flexible, it becomes very expensive very quickly.
Exactly. Yes. No. We've. I think a lot of us have dealt with that in some way or another. It's easy to add too many features, right?
And another problem, sometimes you don't pay this only in utilization, you also pay it in performance. Right.
So do you get any, yeah, so that's a good question. Do you get any estimates of performance as you're making this design?
Well, for now, we have only.
Oh, I think you went on mute somehow. I'm not sure how, because we lost your audio.
If he's not coming back, I can jump in. I don't know. Yeah, but I'm happy to jump in. So I think overall, yes. I mean, I guess that there's two pieces to this, right? Like there's the easy bit is just like synthesizing the thing and getting the number. Does it meet timing? Does it not meet timing? Right? And I guess if it was that easy, then a lot of what we did would probably not be necessary. But I guess the harder bit is really that a lot of this is about the end-to-end performance, right? And this is kind of where we started, right? Because ultimately we were expecting that you will end up with running part of the processing on the host CPU, right, and part of it on the NIC, right? Like you would with RDMA, right? Where so maybe some of the more complex processing for opening and closing connections and stuff like that would run on the host CPU, and other bits run on the NIC, right? Or you handle rare cases on the host, etc., right? And then it becomes complicated. I think that's where a bunch of the complexity came in, where we were looking at these end-to-end simulations, right? Because that really seemed like the only way of even getting close. So basically, what we were able to do there is actually take the synthesized RTL, no, not the synthesized, but the RTL, and simulate that at the frequency that the tool tells us it runs at, and like actually plug it into the full system as a PCI device, right? So we have that working with the baseline corundum, and then we can add whatever processing we want to add on top of that, and see, like we can simulate multiple hosts of this and see what the overall end-to-end performance is, right? With the offload enabled, with the offload disabled, and compare those numbers.
Yeah, I mean, it's nice if you can kind of close the loop, right? You know, you have a vision for what you're trying to design, what you're trying to optimize in the hardware, and you do the initial design, you do some sort of performance estimations, you tweak your design, you know, you iterate, right? But closing that loop can be difficult, especially with all the different tool flows and workload simulations and all of that. Okay, great. So we're actually at time, but if there's more questions, we can keep going in the Q&A and later in the discussion period as well. Thank you very much. I hope that Artem, you can come back from outer space safely and land back on Earth.